In Roman mythology, which of course is rooted from Greek mythology, Juno was the wife and sister goddess of Jupiter. And Jupiter was sort of being naughty with some friends, so he cast a veil of clouds around himself and his friends. But of course Juno was a fairly powerful god herself and used her powers to look right through the clouds and see the true nature of Jupiter and understand what he was really up to. And that's exactly what the Juno spacecraft does for us, is that it goes there with special instruments in a special orbit and uses its powers to see right through Jupiter's clouds and understand its true nature, which is holding these secrets for us about how the solar system formed and where we all came from. Juno spins like a propeller, where the propeller's kind of facing the sun because they're all solar powered.
If you spin something, it stays spinning. It's like a gyroscope. We can use a spinning spacecraft to let each instrument get its turn to see Jupiter. We get to go very close to the planet, inside the radiation belts instead of outside the radiation belt. We're in a polar orbit, so by small adjustments of the timing, we can map the entire planet. We can get repeated stripes at different longitudes as Jupiter spins underneath us.
It does mean that Juno is going to see the polar regions to a greater extent than with other spacecraft, but I think the most important thing is that it gets in very close to the planet as part of that ellipse, brings it in a few thousand miles above those cloud tops, very close, near the equator.
We're going to go over the poles of Jupiter. That means we can study the magnetosphere in a different way.
A magnetosphere is the sphere of influence of a magnetic field. So a planet that has a magnetic field has a magnetosphere when its sphere of influence extends beyond the planet out into space and affects the region around it. The magnetosphere of Jupiter is vast. So if you think of Jupiter being 10 times the size of the Earth, and the magnetosphere is 100 times the size of Jupiter.
I would expect Juno to tell us more about how planets work, meaning how the heat gets out, what kinds of flows exist inside the body, how magnetic fields get generated. Learning what Jupiter is made of, we will learn such a wide range of things. For indeed, Jupiter is the most massive planet in the solar system. It is the body you want to understand in order to understand the architecture of everything else, including Earth.
Humanity has had its eyes on Jupiter for centuries. First, telescopes, and in recent decades, 8 deep space probes were used to examine the largest planet in the solar system. NASA is returning to the gas giant with a large spacecraft called Juno. Equipped with unique sensors, Juno will look deeper into the planet's structure than ever before to find out the answers to basic questions about Jupiter's makeup and how it formed.
Juno's looking for how Jupiter formed and really how planets are made in general. We're very much looking for the recipe for planets. The special thing about Juno is we're really looking at one of the first steps, the earliest time in our solar system's history. Right after the sun formed, what happened that allowed the planets to form, and why are the planets slightly different composition than the sun?
Jupiter is so far away from Earth that even when it's at its closest to us, it will still take a radio signal moving at the speed of light about 34 minutes to cross the distance. Getting Juno on a course to reach the distant planet is the job of an Atlas V rocket, one of the largest in NASA's catalog. It has already been used to loft several NASA missions for the Launch Services Program, including the New Horizons spacecraft on its way to Pluto.
It's flown quite successfully, like I said, the 28 times. Pretty challenging missions, pretty challenging payloads. It's got a heritage that goes back to the Atlas I and some of the components and in the upper stage. So it's an evolution of a family. And in its current configuration and shape and form, I'd say it's pretty robust.
The alignment of Earth and Jupiter leaves the mission's managers with a limited window to launch the spacecraft.
Juno only has a 22-day launch window, or unless we're down for another 13 months until our next opportunity. So it's those kind of challenges with making sure you do all the little things necessary to maximize the opportunities that you get for those 22 days.
Even riding a powerful rocket into space will not be enough on its own to push Juno to its target. The spacecraft still needs the kind of assist only a planet can provide. That's why Juno will go into an orbit that will bring it past Earth 2 years after launch and use the Earth's gravity to slingshot it out to Jupiter, arriving there in August 2016. Aside from distance, Jupiter offers unique challenges to a spacecraft, such as a radiation field rivaled in intensity only by the Sun.
We have a box in the middle of the spacecraft that we call a vault, and it's made out of titanium, and that shields all the electronics from these hazardous radiation. And we're very much an armored tank going to Jupiter.
Just as Juno is building on the knowledge gained with past missions to Jupiter, future missions will build on Juno's findings.
If we can start to understand the role that Jupiter played in how the planet formed and how that eventually governed the creation of the other planets and Earth and maybe even life itself, then we know a little bit about how to look for other Earth-like planets maybe orbiting other stars and how common those might be and the roles that those giant planets that we see orbiting the other stars play.
NASA's Launch Services Program has dispatched several probes to deep space in recent years, including the Opportunity and Spirit rovers on Mars, the Cassini spacecraft that is studying Saturn, and the New Horizons mission that is on its way to Pluto. The schedule does not lighten for the LSP team after Juno. Along with an experimental polar orbiting weather satellite, missions to the Moon and Mars are set for launch this year.
Really, all these missions that LSP is involved in and NASA is involved in are all precursors to the bigger picture of getting humans out beyond low Earth orbit to Mars, to an asteroid and beyond.
For now, though, the team is focused on getting Juno safely on its way to Jupiter.
I will be celebrating when I hear that that spacecraft has separated successfully and those solar rays are out.
Heute Abend soll vom US-Weltraumbahnhof Cape Canaveral aus die Sonde Juno starten. Juno soll, wie hier zu sehen, den Gasplaneten Jupiter 33 Mal umkreisen. Dabei wird sie sich ihm bis auf 5000 Kilometer nähern. So eng wie kein Raumfahrzeug zuvor. Die NASA verspricht sich von der Mission Informationen über die Entstehung von Planeten.
This is Atlas Launch Control at T-minus 2 hours and holding. We're in a planned built-in hold at this time on the launch of the Juno spacecraft aboard an Atlas V rocket. We are now 2 hours, 32 minutes, 32 seconds away from the liftoff of the Atlas V. Liftoff is from Launch Complex 41 at Cape Canaveral. The Juno spacecraft will provide the most detailed observations to date of Jupiter, the solar system's largest planet. Additionally, as Jupiter was the most likely the first planet to form, Juno's findings will shed light on the history and evolution of the entire solar system. The launch window today extends from 11:34 a.m. to 12:43 p.m., a duration of 69 minutes. Following the 5-year cruise to Jupiter, which will include a gravity assist Earth flyby, Juno will enter into a polar orbit around the planet, completing 33 orbits during its science phase, before being commanded to enter Jupiter's atmosphere to complete the mission. Juno will orbit the planet every 11 days, coming as close as 3,100 miles to Jupiter's cloud tops, while measuring magnetic and gravity fields, atmospheric composition, and performing infrared, ultraviolet, and visible light photography. The Juno spacecraft is unique in several ways. It's the first solar-powered spacecraft to perform operations this far from the Sun. To accomplish this, Juno is equipped with 3 very large solar arrays, which, when extended, bring the spacecraft to a total diameter of 66 feet. To combat its exposure to radiation during its year-long orbit of Jupiter, most of Juno's electronics have been housed inside a titanium vault in the center of the spacecraft. Juno will be spin-stabilized throughout its mission in order to maximize the scientific observations. We've had a weather forecast from our launch weather officer, Clay Flynn, and the forecast is essentially unchanged from what we've been watching all week. There is just a 30% chance of not meeting the launch weather criteria. There will be a chance for some isolated showers. Winds will be out of the southeast at around 12 knots, visibility of 7 to 10 miles. Winds generally from the southeast and a temperature of approximately 86 degrees. Mysterious Jupiter is the most massive planet in our solar system. Now, NASA is preparing to send the pioneering Juno spacecraft on a one-year mission to study the stormy gas giant. Its mission? To study Jupiter's core, atmosphere, powerful magnetic field, and auroras, all in hopes of expanding our knowledge of how our solar system formed. Juno is launching from Space Launch Complex 41 at Cape Canaveral Air Force Station in Florida aboard a mighty Atlas V rocket. The spacecraft arrived in Florida inside a U.S. Air Force C-17 cargo plane, touching down April 8, 2011 on the shuttle landing facility at nearby Kennedy Space Center. From there, Juno was moved to the high bay at Astrotech Space Operations in Titusville, where technicians readied it for launch. Several critical pieces had to be installed, including a high-gain antenna used for communications, and all three power-producing solar arrays, which also were deployed and put through illumination testing. As Juno was prepared for liftoff, elements of the Atlas V launch vehicle built by United Launch Alliance began arriving May 23rd. The booster stage arrived at Cape Canaveral Air Force Station skid strip aboard a Russian Antonov cargo aircraft. 2 days later, the Centaur upper stage followed. The Atlas V booster was hoisted into liftoff position inside the launch complex's vertical integration facility on June 13th. Then the rocket's 5 solid rocket boosters were attached. The rocket Centaur upper stage arrived at the launch pad June 24th. But before Juno could join its rocket, it had to pass the spin test, a final check of its weight and balance. Juno was deemed ready to fly, then placed into the 2-piece payload fairing that will protect the spacecraft during the first 3.5 minutes of the climb to space. Early in the morning of July 27th, the fairing containing NASA's newest interplanetary explorer arrived at Space Launch Complex 41, where it awaits liftoff, and a rendezvous in 5 years with the enigmatic planet Jupiter.
LCLD's on and copy that.
Roger.
LCAC.
Go ahead.
Roger, sir. I'm prepared to provide you with a final out brief regarding the higher than normal charge cycles.
Roger, proceed.
Roger. We believe we've isolated the problem to the ground side based on the lockup test. As a precautionary measure, we would like to have the operator switch the vent valve system to the secondary mode using option 360. This is a standard operating procedure. We could be experiencing some bleed through on the primary valve. either way, recommendation would be to switch to the secondary mode and continue with the launch countdown.
Roger. And we would do that switch prior to terminal count?
The sooner the better.
Roger. Understand. And the anomaly team recommendation is to proceed with terminal count?
That is affirmative.
Roger. LC copies and concurs. NASA Launch Manager?
NLM copies and concurs.
Roger. And Launch Director?
Copy and concur.
Roger. Centaur Pneumatics, LC?
Go ahead, sir.
Roger. Please switch your helium charge system to the secondary mode using option 360.
Roger, will go.
And advise when complete.
Copy that.
Launch Director, LC?
LDN1.
Roger. At this time, launch vehicle is ready to proceed with terminal count, just awaiting your direction for a new T0.
Roger. All issues are resolved, and we are standing by here on SCOBOX.
Roger.
LC, the helium bottle vent valve is switched to secondary.
Roger.
This is Atlas Launch Control, T-minus 4 minutes and holding. As we've heard, we've cleared our technical issue, and the only thing remaining is to hear from the range that there are no remaining boats in the launch danger area, and as soon as the range gives us a green, then we will determine our new T0 time and continue on down toward a launch today. We still have about 39 minutes remaining in our launch window. At T-minus 4 minutes and holding, this is Atlas Launch Control.
Launch Director, LC?
Go ahead, LC.
Roger. At this time, recommend extending the hold an additional 5 minutes.
Copy and concur.
Roger. Com, LC?
Com on 1.
Roger. Extend the current hold an additional 5 minutes.
Roger, and work.
LC, LD, Channel 1.
Go ahead.
This time, LC, please put into work a target of a new T0 of 1613 Zulu.
Roger, copy 16:13 Zulu.
Good copy.
Roger. Range coordinator, LC.
LC, range coordinator 1, go ahead.
Roger, please coordinate a new T0 of 16:13 Zulu.
Roger, 1613 ZN work.
Roger. Com, LC.
It's comma 1.
Roger, please set the countdown clock for a new T0 of 16:13 Zulu.
Roger, 16:13 Zulu.
This is Atlas Launch Control, T-minus 4 minutes and holding. As we've heard, adjusting for the time they give as Greenwich time, our new T0 is going to be 12:13 p.m. Eastern Time, assuming that the range can give us a clear to launch by that time. And we should be getting a poll from the NASA Launch Manager in just about 1 minute. Again, the only issue now is waiting for a range clear to launch.
This is the NLM on the NLM net for a final launch poll and ready to release the hold at T-minus 4 minutes. Currently working to a T0 of 1613 Zulu. NASA CE. NASA CE, this is the NLM on the NLM net. NASA CE, this is the NLM on the NLM net.
NLM, this is CE2. On Net 4, CE is likely still engaged in the anomaly discussion. I recommend we delay this poll as far as possible.
NLM NASA CE on your net.
Go ahead, NASA CE.
I heard you were calling.
Yes, sir. We were polling to release the hold at T-minus 4 minutes. You ready to go?
No, we're still working this item.
Still working an item.
Correct. Yeah, so no, we are not ready to come out of the hold.
I copy. No go.
Okay, as we heard, NASA Engineering is still discussing the circumstances and is not ready to give a go for launch yet.
Our switches are in the proceed position.
Ready to proceed.
Roger.
Like the range very shortly will be able to give us a go.
LC, LD, channel 1.
Go ahead, LD.
Please extend the hold additional 5 minutes.
Roger. Com, LC.
It's Comma 1.
Roger. Please extend the current hold an additional 5 minutes.
Roger, 5 minutes.
This is Atlas Launch Control, T-minus 4 minutes and holding. With that, an additional 5 minutes extension. That would put our liftoff time at 12:18. And basically the anomaly discussions just simply did not finish in time to be able to give a go to make the 12:13 launch time, but those discussions are wrapping up. And so 12:18 appears that is probably going to be our new launch time. We'll stand by for confirmation of that. And at T-minus 4 minutes and holding, this is Atlas Launch Control.
LCAC.
Go ahead.
Roger. There was extensive discussion on the engineering net to ensure that we understood the ramifications of the leak on the ground side to make sure that it wasn't going to have any negative repercussions. This was not held as an anomaly discussion, just as an engineering evaluation. The team has determined that we have plenty of margin and that with Redline Monitor protecting us, that we are ready to proceed.
Roger.
No issues.
Roger, understand. Launch Director, LC.
Launch Director on 1.
Roger, standing by for direction on a new T0.
Roger, LC, at this point the booster vehicle is cleared for flight.
That's affirmative.
No issues are being worked.
That's affirmative.
Roger, stand by for new direction.
We're still at T-minus 4 minutes and holding. Confirmation that the range has given a go, that the boats in the area are now out of the launch danger area. And it's appearing that we may extend once again to give the NASA and associated engineering teams time to reach a firm conclusion on the issues that we've been working. They're getting very close to that. Meanwhile, the Juno spacecraft remains on external power. Appears we may be going toward a 12:25 liftoff now, but that's not confirmed.
1.
Go ahead.
LC, please put into work a new T0 targeted for 1625 Zulu. 1625 Zulu.
Roger, copy 16:25 Zulu.
Good copy.
Roger, range coordinator LC.
LC, range coordinator 1.
Roger, please coordinate a new T0 of 16:25 Zulu.
Roger, 16:25 Zulu, in work.
Com LC.
It's comma 1.
Roger, please set the countdown clock for a new T0 of 16:25 Zulu.
Roger, 16:25 Zulu.
And there we have our confirmation that 12:25 is our new launch time.
LC Range Coordinator 1.
Go ahead.
New T0 of 1625 Zulu has been coordinated and approved.
Roger. All stations maintain your readiness to support of T0 of 16:25 Zulu.
Comp check channel 1.
Read you loud and clear.
Hold to launch to remove the hold at T-minus 4 minutes. NASA CE.
NASA CE is go.
NASA MIM.
NASA MIM is go.
SMD.
SMD is go for final count.
SMA.
SMA is go.
NAM.
NASA advisor team is ready.
Copy that.
And that's our final poll from Omar Baez, the NASA launch director, that he'll pass along to United Launch Alliance that NASA is ready to proceed. Again, we're targeting a 12:25 launch time.
NSC, LC on channel 1.
Go ahead.
Spacecraft to internal power.
Roger.
Flight control, LC.
Go ahead.
Configure Centaur main vehicle battery heaters for launch.
Roger.
And we're standing by now to pick up the countdown. Approximately 15 seconds, we should be resuming.
Centaur main vehicle battery heaters are configured for launch.
Roger.
They're resetting the countdown clocks here in the Launch Control Center to make the final
Red line monitor
adjustment.
and event table are in the correct configuration for terminal count. Roger. All steps prior to the status check are complete.
So that would put us about 7 minutes from launch. And Spacecraft Project Manager Jan Chodas has just confirmed to NASA Launch Manager Omar Baez that
Status check to
Juno
proceed
is
with terminal
go for
count.
launch.
Atlas systems, propulsion,
Go.
hydraulics,
Go.
pneumatics,
Go.
LO2,
Go.
water,
Go.
Centaur systems, propulsion,
Go.
pneumatics,
Go.
LO2,
Go.
LH2,
Go.
has gas,
Go.
electrical systems, airborne,
Go.
ground,
Go.
facility,
Go.
RFFTS,
Go.
flight control,
Go.
instrumentation,
Go.
comm,
Go.
GCQ,
Go.
umbilicals,
Go.
ECS,
Go.
redline monitor,
Go.
quality,
Go.
OSM,
Go.
ULA safety officer,
Go.
range, weather, and final clear to launch.
Go. LC, LD, channel 1.
Go ahead.
LC, you have permission to launch.
Roger, proceeding with the count.
LC, NSC on 1.
Go ahead.
Juno is on internal power.
Roger.
And we should be about 2 minutes now from picking up the countdown.
T0 is planned for 16:25 Zulu. Set count to start at 16:21 Zulu.
Roger. T0 is set for 16:25 Zulu. Count will start at 16:21 Zulu.
Now our clocks are in sync. We should be picking up the count in about 90 seconds. And we'll pick up now in 1 minute. Thirty seconds from picking up the count.
On my mark, time will be T-minus 4 minutes and counting. 3, 2, 1, mark. T-minus 4 minutes and counting.
3:55.
Ground pyros enabled.
Headed for a launch time of 12:25.
Three minutes. Securing LO2 topping. Atlas takes to flight pressure. 250.
Yep, just internal.
2 minutes.
Vehicle internal.
155.
Launch sequencer start.
150.
Securing Centaur LH2.
Securing Centaur LO2.
140.
Launch enabled.
T-minus 25 seconds. We'll get the final go from both Atlas and Centaur. Flight termination system is armed.
$120.
Orca's armed.
FCS count started.
115.
Reduce ECS for launch.
Roger.
110.
Vent valves locked.
T-minus 1 minute and counting.
$49.
T-minus 45 seconds.
Stable at step 3.
T-minus 30 seconds.
25.
ECS reduced for launch.
Roger. Status check.
Go Atlas. Go Centaur. 20.
T-minus 15 seconds. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition and liftoff of the Atlas V with Juno on a trek to Jupiter, a planetary piece of the puzzle on the beginning of our solar system.
PTR roll program is in progress. Vehicle body rates look good. Booster PU has gone to fixed angle for burn. SRB chamber pressures have plateaued. I'm rolling off. Signatures look good. RD-180 operation looks excellent at this point in the flight. Mach 1. SRB chambers continue to roll off. Max Q. Boosters throttling up, right on schedule. Engine response looks good. Booster P's gone to closed loop control. Looking for our SRB throttle down momentarily. Engine continues to operate well. And booster has throttled back. Looking for SRB burnout soon. Chamber pressures have plateaued on the SRBs. And we're beginning to roll off. And BOTA has been satisfied. Vehicle is throttling back up to full thrust. And we have solids 1, 2, 3, 4, and 5 jettisoned. Visual indication that all solids have separated well. And the booster has begun its roll for spacecraft thermal constraints. Rates look good. Bus and battery voltages are stable. And the vehicle has now gone into closed loop steering. And booster PU is also on closed loop control. Engine response looks good for the set mixed ratio. Current altitude is 45.8 miles in altitude, downrange distance 69 miles, velocity 5,413 miles per hour. Coming up on our RCS pyro valve activation. It is now fired. System's now pressurizing to flight levels. We've begun our 2.5 G throttle segment. Engine response looks good. Current altitude is 60 miles in altitude, downrange distance 118 miles. Velocity is 6,983 miles per hour. Coming up on our next mark event will be payload fairing jettison, followed by the CFR jettison. And we have payload fairing jettison and CFR jettison. Boosters throttle back up to full thrust. Engine response looks good. Now accelerating at 4.7 Gs as we work our way to our 5G throttle segment. Boost phase cooldown is underway. Now throttling to maintain 5 Gs. Pogo pyro vent has been fired. And begun throttling to 4.6 Gs in preparation for BECO. Boost phase cooldown is complete. We have BECO. Engine shutdown looks good. We have retros and stage separation. We have LOX and fuel pre-start. RCS GN2 purge firing is underway. We have ignition and full thrust on the RL-10. Small body rates associated with closed loop steering. Vehicle tank pressures are being ramped down as expected. Centaur PU has been commanded to oxidizer-rich fixed angles for the early part of this 6-minute and 2-second burn. Current altitude is 112 miles. Downrange distance is 589 miles. Velocity is 14,318 miles per hour. Range track shows the vehicle right down the middle of the corridor, making excellent progress. Centaur tank pressures are very good at this point, holding expected levels. Storage bottle pressures are as expected. Bus and battery voltages look good.
Just acquiring the signal.
And we're seeing our phase 1 thermal conditioning firings on the RCS. Line temperatures look good. Centaur is now operating in closed-loop PU control. However, it continues to request an oxidizer-rich condition as it works off the excess oxidizer. RL-10 engine operation looks good as we have a momentary loss of data. Right where the format change is supposed to happen. And we have resumed Centaur telemetry. At this point, the MDU format change should have occurred.
Loss of signal here at the Cape and Jupiter Inlet. Antigua now with data.
The RL-10 continues to operate very well. Current altitude is 134 miles. Downrange distance is 1,081 miles. And current velocity is 15,339 miles per hour. And we're seeing another RCS thermal conditioning firing as the line temperatures warm towards bottle temperature. Signatures look good. Centaur continues to request an oxidizer-rich condition. With a little over 2 minutes remaining in this burn, all Centaur systems look nominal. RCS line temperatures have now warmed to bottle temperatures as expected. RL-10 continues to operate well in an oxidizer-rich condition. Centaur mass error is approximately 500 pounds. One minute to MECO. All Centaur systems continue to look excellent. And we have IAP vanish coming up on MECO momentarily. And we have MECO. Engine shutdown looks good. We have 4S settling on. RF has been disabled.
Rob, can you give me orbits? I've got the full back screen.
And Centaur has begun its turn to its PTC attitude. During the PTC roll, it'll be rolling at 3 degrees per second. Fuel tanks have been vented down, and we continue to settle in a 4S mode. And Centaur has now achieved the 3 degree per second roll rate for the PTC and continues its slow turn to its PTC attitude.
Rob, it was expected to be 104 by 121.2.
Data now coming through the tracking data relay satellite. We've had loss of signal at Antigua.
Quick check of the orbits shows that Centaur is exactly where we wanted it to be.
With the cutoff of the Centaur and
Centaur has begun venting the fuel tank down to condition propellants during the coast phase.
with the Centaur now going into the coast phase, it's a 31-minute coast phase that began with the cutoff of the Centaur engines. Centaur will restart 41 minutes 33 seconds into the mission for a second 9-minute burn. So while we're in the coast phase, we're going to look now at some of the replays of the launch from the different angles around Kennedy Space Center, Cape Canaveral Air Force Station, and our long-range trackers.
That latch and this latch. This head six. Do we have another one? No, that's the only one that holds on. All Centaur systems continue to look very stable as the PTC attitude change continues. And Centaur has completed its orientation to the PTC attitude during the coast phase. All systems continue to look excellent. And Centaur has begun to ramp the 4S settling motors to a 25% duty cycle. Signatures look good. All Centaur systems continue to look good. Data quality is very good at this point in the mission as we continue to ramp down to the 25% duty cycle on the RCS. We're now 10 minutes into our 30-minute coast between MECO 1 and MES 2. All systems continue to look good as the RCS continues its ramp down to 25% duty cycle. And Centaur has now achieved the 25% duty cycle on the RCS. All systems are stable. Helium storage bottle pressures look good. Plus and battery voltages are stable. Centaur is now halfway through its 30-minute coast, continues to roll at 3 degrees per second in its PTC attitude. RCS is operating at a 25% duty cycle. Tank pressures are stable. Storage bottle pressures are as well. Plus and battery voltages look good. And we have had our LO2 LOX duct flush. Signatures look good. Centaur has now begun its PTC roll reversal. And Centaur has completed its PTC roll reversal. It's now rolling at minus 3 degrees per second. Centaur is now 2/3 of the way through its 30-minute coast period. Continues to roll at -3 degrees per second in its PTC attitude. RCS continues to operate at 25% duty cycle. All Centaur systems are operating nominally at this point in the flight. Telemetry data quality continues to look pretty good with some minor interruptions. In about 30 seconds, we expect to see Centaur begin its turn to MES 2 attitude and begin 50% duty cycles on the RCS. And Centaur has begun to reorient to the MES 2 attitude, and RCS is now operating at a 50% duty cycle in preparation for MES 2. 5 minutes to MES 2. We are experiencing some data dropouts associated with the PTC roll and the turn to MES 2 attitude, but all systems continue to operate well. And Centaur has begun 4S settling, and it's also begun to despin from its PTC roll. And Centaur has completed its despin from the PTC roll, and it is continuing to reorient to its MES 2 attitude. And Centaur has now achieved its MES 2 attitude. Just about 2 minutes to MES 2. And Centaur has begun the pressurization sequence in the fuel and oxidizer tanks for MES 2. Tank pressures look good. One minute to MES 2.
That is the restart of the Centaur. For a second burn that will last about 9 minutes.
We have fuel pre-start. Oxidizer pre-start. We have ignition and full thrust on the RL-10. This is an expected 9-minute and 3-second burn. Centaur PU is now in closed loop control. RL10 chamber pressures look very good. Turbine temperatures as expected for the set mixture ratio. And we are seeing hydrazine burn-off occur, increasing upper stage performance. Centaur PU continues to command an oxidizer-rich condition. PU mass error is approximately 250 pounds. RL10 continues to perform very well. LOX pump discharge pressures, fuel vent inlet pressures are within expected parameters. PU is now commanding a slightly more nominal mixture ratio as the mass error is being reduced towards 0. Centaur continues to have hydrazine burn-off sequences occurring. Signatures look good. And the burn-off phase has been completed. Centaur is currently accelerating at 0.69 Gs. Data quality remains good. Engine operation is as expected. Hydrazine line temperatures are reading bottle temperatures as well. It's nominal for that system. Five minutes remain in this 9-minute burn. And Centaur PU is now operating at nominal mixture ratios as the mass error is reduced to 0. And we continue to see our normal hydrazine thermal conditioning cycles. Signatures are typical. PUs continuing to operate near nominal mixed ratio. Engine performance remains very good. Three minutes to MECO. Centaur's continuing to accelerate, now currently at 0.95 Gs. Two minutes to MECO. One minute to MECO. RL10 continues to perform well. Centaur PU error is 0. Now controlling at nominal mixed ratio. Coming up on MECO momentarily. Engine continues to operate well. And we have engine shutdown. Shutdown looks good. 4S settling has begun. And Centaur has begun its turn to spacecraft separation attitude. Coast phase between MECO and spacecraft separation is scheduled at 3 minutes and 15 seconds. Centaur tank pressures are stable, bottle pressures look good. Bus and battery voltages are stable as well.
Everyone here in the Launch Control Center now awaiting spacecraft separation.
31.1.
Centaur reorienting for spacecraft separation.
57.3. DLA 19.6. Basically right where we plan to be. Centaur is now settling at 50% duty cycle. And Centaur has completed its turn to spacecraft separation attitude. Prior to separation, Centaur will spin up the spacecraft at 8.4 degrees per second.
And we're less than a minute away from spacecraft separation.
And Centaur has begun the spin up of the spacecraft for separation.
LCSE.
Centaur's achieved spin rate, and we have spacecraft separation. This concludes the plus count commentary for the AV-29 Juno mission.
This is Atlas Launch Control. We'll be standing by now for a short interview with Omar Baez, the NASA Launch Director for today's countdown. The official liftoff time was 12:25:00.146. That was first motion of the Atlas off the pad at Complex 41, 12:25:00.146. And at this time, we have every indication that we've had a very successful flight of the Atlas V, Atlas Centaur rocket. Joining us here in the Atlas Spaceflight Operations Center is Omar Baez. Omar was our NASA Launch Director for today's flight. And Omar would like, first of all, to tell us your assessment of how the flight so far looks.
Flight so far looks fantastic, George. The spacecraft did separate. It's in the right orbit to head to Juno or start its journey to Juno. Jupiter. Excuse me, the excitement got me there. And yes, we are right on track for that, and everything looked good.
The last part of the countdown was a little interesting, and maybe you could explain more in layman's terms what was actually going on there that pushed us out while we looked at this issue.
Yeah, we had an issue with one of our helium bottle charging circuits that started to cycle quite a bit. Cycling means that it's trying to charge our onboard bottles to maintain pressure. Well, it turned out we isolated it to a leak on the ground side. The flight bottle was fine. We had the proper mass to do all our control actuations that we need in flight from those bottles. So we isolated it to the ground system. There was some additional questions, and it drove us to start consuming some of the window. And we ended up consuming roughly 51 minutes of our window there.
Now tell us why that system is important. Why was the launch team concerned?
Well, that system basically controls the pneumatic functions of the Centaur. In other words, if we're gimbling the engine or shutting off valves or energizing valves, this is a pneumatic system that not only provides that pressure but also helps in pressurizing the tanks and keeping the tank pressures up. So it's how we store our helium commodity on board.
Well, it appears, Omar, that with a good flight underway, there's another Atlas right on the heels of this. What's about to come out to Complex 41?
Well, we're going to have our Atlas and Centaur vehicle for the MSL mission, which we're launching in November. And we're looking forward to getting that work done. But before we do that one, we have Grill coming up inside of a month here, and work on that mission is ongoing right now at Complex 17. And as soon as we're done with that, we shift gears back to the West Coast to do the NOAA or the NPP mission at Slick 2 on a Delta II before we get back to MSL.
Vandenberg. So this is quite a year of high-profile missions for us. So, well, Omar, it's good to be able to congratulate you and the NASA and United Launch Alliance team, because this appears to have gone very well for everybody, and I'm sure that very shortly we'll hear some very ecstatic remarks from Scott Bolton, our principal investigator. So, Omar, thank you very much, and we'll look forward also to talking with you when we get to Mars Science Laboratory.
Okay, George.
6,
evidence
5,
of flow.
4,
Let's listen in.
3, 2, 1. Ignition and liftoff of the Atlas V with Juno on a trek to Jupiter, a planetary piece of the puzzle on the beginning of our solar system.
Pitch yaw roll program is in progress. Vehicle body rates look good. Booster PU has gone fixed angle, show the confirmed. SRB chamber pressures have plateaued. Gone rolling off. Signatures look good. RD-180 operation looks excellent at this point in the flight.
Absolutely exciting mission, a successful liftoff by another unmanned solar-powered spacecraft called Juno. 5-year mission. They say Jupiter holds the secret to understanding how all of the planets work. You're watching BBC World News.
2, 1, ignition and liftoff of the Atlas V
just launched
with
its
Juno
spacecraft Juno on a 5-year journey to the planet Jupiter. The U.S. Space Agency says Juno will offer a unique look at how the solar system was formed.
Auf zum Jupiter. Vor knapp einer Stunde startete in Cape Canaveral die Sonde Juno zum größten Planeten unseres Sonnensystems. 5 Jahre wird die Reise dauern, angetrieben durch die Energie 3er Sonnensegel. Juno soll dem Jupiter so nah auf die Pelle rücken wie keine Sonde zuvor. Die Wissenschaftler der NASA erhoffen sich Informationen zum Ursprung unseres Sonnensystems. Außerdem wollen sie wissen, ob der Gasriese Jupiter überhaupt einen festen Kern hat.
Die US-Raumfahrtbehörde NASA hat heute eine Sonde auf den Weg zum Jupiter geschickt. Bis 2016 soll Juno dorthin unterwegs sein und den Planeten dann 1 Jahr lang umkreisen, unter anderem um die Struktur und die Atmosphäre zu untersuchen. Die Mission soll neue Erkenntnisse darüber liefern, wie unser Sonnensystem entstanden ist.
Die Atlas-Trägerrakete auf dem Weg zum Startplatz. 770 Millionen Euro kostet die Erkundungsreise der Sonde Juno.
2, 1, ignition.
Der Start dann mit einstündiger Verspätung, weil es Probleme mit der Heliumversorgung gab. 5 Jahre wird Juno unterwegs sein, bis sie nach 2,7 Milliarden Kilometern Jupiter, den größten Planeten unseres Sonnensystems, erreicht hat. Junos Energieversorgung gewährleisten riesige Sonnensegel, ein Novum bei solchen Fernreisen. Der Gasriese Jupiter könnte helfen, die Anfänge unseres Sonnensystems 5 Milliarden Jahren besser zu verstehen. Wie eine Zeitmaschine hält er dank seiner immensen Anziehungskraft all die Partikel fest, die damals auch zu seiner eigenen Entstehung führten. Die Hoffnungen der NASA, Anders als Junos 8 Vorgänger wird diese Sonde nicht nur vorbeifliegen, sondern ein Jahr lang um den Riesen kreisen, so nahe, dass eine Titanhülle die Instrumente vor Jupiters gewaltiger Strahlung schützen muss. Hat Jupiter einen festen Kern? Welchen Wassergehalt hat seine Atmosphäre? Antworten darauf und viele schöne Fotos soll Juno zur Erde funken, bevor sie nach einem Jahr planmäßig in den Planeten abstürzt.
Trotz der Börsen, mit denen wir heute begannen, es soll niemand sagen können, dass dies ein Freitag war, an dem alles abwärts ging. Am Cape Canaveral hob eine Atlas-Rakete, das alte Arbeitspferd der NASA, einen Satelliten in den Weltraum. Auf eine lange Reise zum größten Planeten unseres Sonnensystems. Hildegard Werth berichtet.
5 Jahre wird Juno unterwegs sein, bis sie im Juli 2016 beim Jupiter ankommt. Es ist eine Distanz von 675 Millionen Kilometern, mehr als 4-mal so weit wie die Distanz Erde-Sonne. Jupiter ist der bei weitem größte aller Planeten. Man nimmt an, dass er vor allem aus Wasserstoff und Helium besteht. Auffallend ist der große rote Fleck, ein Sturm, der seit 300 Jahren an der gleichen Stelle tobt. Was sich darunter verbirgt, ist immer noch ein großes Rätsel. Juno soll herausfinden, ob der Gasriese vielleicht doch einen festen Kern hat und ob es in der Jupiteratmosphäre Wasser gibt. Dazu muss sich die Sonde bis auf 5000 Kilometer gewissermaßen hautnah an den Riesenplaneten heranpirschen. Wir müssen dicht an Jupiter herankommen, auf die Innenseite seiner Strahlungsgürtel. Gegen die intensive Strahlung muss die Sonde besonders geschützt werden. Wir haben eine Box in der Mitte, die wir Tresor nennen. Die ist aus Titan und schützt die Elektronik vor der gefährlichen Strahlung. Mit ihren Solarzellen, die an Windmühlenflügel erinnern, soll Juno den Planeten 33 Mal umkreisen. Der Kurs führt über die Polregionen, von denen man bisher nur wenig weiß. Junos Ende ist vorprogrammiert. Nach einem Jahr wird sie in den Jupiter hineinstürzen und ein Teil von ihm werden.